Okay, so in the last class, we understood and we learned about the electronic configuration using the Aufbau's principle and the Bohr-Bury's principle. Let's start today by trying to write the electronic configuration for chromium, which is 24, and copper, which is 29. What's the Latin name for copper? And YCU.
What's the what?
What is the Latin name for copper? Cuprum. So that's the Cu. Sodium is natrium, potassium is calcium, things like that. So. Lauren, do you have it? Do you want to try? Hey? Just give it a shot. I mean, I did it wrong the first time, so there is no harm in doing it wrong. I mean, so you understand, like this has something special going on, and that is why I told you to write it. So it might not be that usual. So, but let's try.
1s2, 2s2, 2p6, 3s2, 3p6, and then let it go 4s2, 3p4.
Okay. Who has it? All of you? Does anyone has anything different? So by same logic, this becomes this, right? It's just 29. So 4 goes there, and here 9. Okay? But the thing is, it's not the electronic configuration. Does anyone have anything different? Can you think, now that I told you this is not the right ones, can you come up with something that, so see, nature doesn't exist like this. Nature wants what? What does nature want? What does anyone want?
Stability.
Yeah, so how do you get like a more stable, can you get a more stable form? Just guess. So this is take an electron from whom? So then it becomes a negative. So let's not exchange electrons from someone else. Let's rearrange the electrons that we have got in ourselves. What would you do?
Put one from 4s into 3d.
Yes. So nature did this to make itself more stable. So there is an energy associated with this transfer, because when you're taking some electron and putting it some other, there is an energy involved. So because this was full filled and this was partially filled, now we have two half fills. So there is an energy, somehow the two half filled got favored over one full and one partially filled. So there is an energy that we can actually calculate it, but I'm not going into that. How do you exactly calculate this? These two are some of these examples in which 4s2 3d4 is not favored, 4s1 and 3d5 becomes favored, and for chromium. Hunter, do you have any?
So I guess the point is to at least get it half filled if it's already partially filled.
Yes. Yes.
Can you explain how you got 4s2 3d9?
Oh, here?
Yeah. Whenever you break it up to, I guess, get rid of the first ones, how do you get 4s2 3? How do you get 3d9? That's my question.
Sure. Okay, what would you suggest? Now this is actually 4s2 3d10, but That's the next step.
That's like the filled.
Yes, yes. But you have doubts in 4s2 3d9. Do you have doubts in 4s2 3d4? How do you got that?
No.
From Aufbau? So then why do you...
So okay, so essentially you're taking one electron from 4s2,
Sorry. Yeah.
and then essentially you're moving it over to the 3d orbital, which gives it 3d9. Oh,
3d10.
3d10, yeah.
Yeah.
Okay.
Yeah. So basically, you went from the stability of this thing was more important. So this was partially filled, this was full filled. You chose, or nature chose, a half filled and a full filled. So basically, there's no partially filled orbital now in this one, but there is a partially filled orbital here.
Okay.
Does the logic fit?
Yes.
Okay.
But does that still the first one that we wrote out, that still qualifies as your orbital electron configuration. So is it technically correct?
This is the correct one. This is not the correct. This is not how we represent the electronic configuration of chromium. You would think this would be by Aufbau's rule,
Yeah.
right? That's why I'm discussing this, because you would think this is the correct, because if you just follow Aufbau's rule, this is the configuration. But now if you think about the overall stability and bring in one more additional factor of the half-filled and the full-filled and the partially filled orbitals, then this.
So then, so then these
Yes.
are specified to do the Aufbau principle for electronic configuration, and then I guess how would you fill the electron orbitals afterwards to make it more environmentally correct, or
See, the thing is, Aufbau principle is helping you to write the electronic configuration, right? Now, the principle is based on the n plus L rule, right? Now, that is a good first principle to get you the configurations, right? But then, certain things are not that simple that can be explained just by the Aufbau's principle. Because Aufbau's principle is not telling you Aufbau's principle does not tell you that a P5 or a P4 is this or this.
gotcha.
Right?
Gotcha.
It's just telling you it's P4. So in here, you need to understand this rule, the Hund's rule of maximum multiplicity. You have to add another layer to the electronic configuration to accurately get it to these.
Gotcha. Okay.
So you get like a first pass and then actually get the exact
Aufbau
ones.
is essentially like your baseline.
Yeah,
Gotcha.
yeah, yeah. And then so from here,
Then you want to make sure you fill your orbitals. Okay.
yeah. So for here, the P4 still this is definitely incorrect. So you are absolutely not doing this. You are doing this. But in here, even the D4 versus D5 is not. So D4 is Aufbau. This is not Aufbau. But when you get in the Hund's rule of maximum multiplicity, which actually is saying, when Courtney said she's more willing to share the room, this is the maximum multiplicity that you would want.
Y'all never heard of the pair rules? You never go anywhere without your pair? Come on.
Yes, but if you do not know anyone, let's assume that.
Okay.
That rule might be, so Courtney rule can be valid for actually going to a vacation, but the Hund's rule of maximum multiplicity actually applies for electrons. So this one is incorrect, and this one is incorrect. For copper, it becomes 4s1 3d10, and this becomes 4s1 3d5 because of this maximum multiplicity rule, which tells you to fill in this order. You increase the multiplicity after you occupy each orbital first and then pair up. So that is the Hund's rule of maximum multiplicity. We saw this rule the last time, but we didn't put a label to it. So here's your label. So it's just a rule. Okay? You can actually calculate the energy. So see, when you went from 4s2 3d4 to 4s1 3d5, that electron must have jumped. So that must have taken some energy to jump. So there must be some energy. This is the energy that must have been required, right? So the atom probably needed that energy, right? So you have an atom, say you have that chromium atom, right? So it needed this energy to jump its electron from this to this, right? So energy, when you need energy, when you take energy, what happens to your energy? It increases. So its energy must have increased. But because of this thing, because you went from a partially filled to a full, to a half filled, that stability must have decreased your energy, right? So the decrease in energy that happened because you reached a half filled in here, the decrease in energy was more than the increase in energy, and that is why there is a net negative, right? So there is a net stabilizing effect. So if you were here and you increased so you got some energy, you jumped your electron from this to here, that required that energy, so you increased the energy, but because you jumped it and made this one more stable, you decreased its energy even lower than this level. And therefore, the overall effect is negative. It's like a stabilizing effect. You can actually calculate those energies. I'm not doing it because that's out of scope. Okay? Jocelyn, is it clear? Okay, any doubts? Cool. Okay, cool. No doubts is good. Having doubts is better. So, okay, so this was one of the trickier ones. So copper and chromium electronic configuration.
I have a question.
Yes.
So if it's like Cu2 minus, are you going to take the electrons from the...
Now the thing is, do you actually get Cu2 minus? You get a plus. Because copper, now this will also come in when we are thinking about electronic configuration on the periodic table. So you imagine the periodic table, right? So we have the periodic table here. On the left-hand side, where do you have the metals? Do you know where the metals are? Towards the right. Okay, let's quickly draw this.
Are they in the middle?
They are, some of them. Yes. There are also some on the right, but how? So, okay, now.
Here you have your noble gases on the very end.
Yep.
And then somewhere in between.
Yep. Now, this brings us to the concept of electronic configuration and the things that will form the cations, the things that will form the anions, and why will an element form a cation or an anion or an ion? Why will an element form an ion?
More stable.
To become more stable. Tiffany, what?
I was saying the amount of electrons like would make it either positive atom or...
Yeah, but why did it go for the exchange. Right, so let's take, so this is the, so hydrogen, helium, oh, sorry. Did you guys watch chapter 8? So this was dealt there, but let's okay, so this is 18, 17, 16, 15, 14, 13, 1, 2, and there are more in here. Okay, now this is the middle one, this is the leftmost. In here you have these, and then you have some in here. Okay? Tell me which is S block. What is S block?
1 and 2.
Why? Yeah, you're right. This is S block.
It's the one that it has the.
It's okay if take a guess. It's okay to be wrong. I am wrong all the time. When I was doing my PhD, the first one lab notebook, which is 150 pages, were just failed experiments. And the Nature paper that we are reading, the Nature Geoscience paper, I started the experiments of that paper in 2018, January, and I got the first correct results in 2021. So this is all wrong things that I was doing. And it got published in 2023. So it took me 5 years to get from of doing experiments to actually publishing the results. So science is a lot of wrong assumptions and wrong. Just tell an incorrect answer.
See, I just hate that. I hate saying things when I don't know if it's right or not.
And you, being in the sciences, you have to be comfortable being wrong, right? Just give me a wrong answer. Okay, come on. You get points for being a wrong answer.
I want to think about it a little bit before I say that's the problem.
Intuitively, what do you think? So this is S block. Okay, what's this? What's this chunk? P, yeah, it's P block. This chunk in the middle, D. And here, F. Why? Yes.
Isn't it like the outer shell, like how much electrons they can fit in there? Or something like that?
It is something related to the electronic configuration, yes.
Well, because it's what we did last class, and so that's why I'm trying to figure out the right way to say it.
Okay, let's.
Valence electrons?
It is related.
Orbits?
Sorry.
Is it the orbits?
What?
Max number of orbits per group? Is that what the periods are looking at?
So let's draw the let's write the electronic configuration. Say let's sodium. So 11, 1s2, 2s2, 2p6, 3s1. Okay. Let's go for calcium. 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What's the similarity?
They end in an s orbital?
Sorry?
They end in an s orbital?
Yes. The last electron, where is it going? That's it. So in here, the last electrons, I guess all of you were kind of like going in that direction. But that's the thing. Like, we always are concerned about the last electron, the valence shell, the valence electrons. That's the most interesting electrons, generally speaking. So the last electrons of all these are coming in and sitting in the s orbital. And now you know what all these things have in common without even writing the configuration. You know for sure that the last electron is coming in and sitting in the sitting in the p, last in the d, last in the f. And that's the power of the periodic table. Doubts?
No, but right.
It's a good way to double check your work.
Yes. Take anything, just pick anything and...
Uranium. I'm kidding.
Sorry?
I said uranium, I'm kidding.
So, and that's another thing, like when you have something, say uranium, I don't know what's, I know 232, 233, 235, those are the mass numbers, but what's the, I don't know. Now, if you want to check where this thing sits, all you have to do is just write the electronic configuration, and you know where it sits. And now let's understand. Now, keep in mind the octet rule, okay? Generally speaking, the octet rule is valid, okay? Now, for example, sodium, if this wants to become stable, what will it do? Tiffany? You know for sure, right? It will lose an electron and become Na+. Can you say the same thing for all these group 1 elements? So all of them, when they will want to achieve stability, they will lose electron. And how many electrons will they lose? Just one. And that's the power of the periodic table. You do not have to write the electronic configuration. Just by this thing being in the same group, so all these vertical columns are called groups, and the horizontal rows are called periods. So anything that is in the same group, they will always have the last same number of valence electrons. So group 1 means 1 valence electron. And that means to gain stability, they will lose 1 electron to become stable. And they will always be a unipositive cation. They cannot be a dipositive. Which ones will be the dipositive?
Group 2.
Group 2. All of these are +2. Now, let's move into to the P block. What is the group 18 doing?
Chilling.
Yes, why?
Because they have their
So they won't form a cation or an anion in normal conditions. Okay? But what is group 17 going to do? So this group 18 is called noble gases, because all of them are gases and all of them are noble. They're not reactive under normal temperature pressure conditions, but they're not inert. They will react when pushed. They're noble, but they are not cowards. They will fight back when time comes. Okay? So we went from inert to noble gases. Okay? Now these two are metals. Right? So these all are metals, and generally you will see the metals forming cations. So generally metals have the tendency to lose electrons and form cations. So all these are metals. When I say all, just keep in mind there might be some here and there might be some oddities. Yes.
Why isn't in physics they teach anything over lithium is a metal?
So in astronomy, like anything over
Anything over that?
hydrogen and helium, it's a simplification. It's a simplification. It's a good question. So in astronomy, when you go take their courses, anything which is not hydrogen and helium, they call it a metal. It's a simplification. Because most of our solar system is hydrogen and helium, almost like 99%. So they just say, okay. It's a form of reductionism if you go to philosophy. So when you think about Japan or India, what comes to mind when you think about India?
Overpopulation.
Overpopulation.
Great food.
Great food. Okay.
It's such a big country, like I got multiple things.
Yeah.
History, metallurgy, Hinduism, ancient culture. I mean,
Right.
it's a lot.
What comes to mind when you think about Japan?
Tokyo. I said Tokyo.
Tokyo. Okay. Yeah. What else? Culture. But that is true for any. But are there other specific things that are coming to your mind, like when you just think about
Samurais.
samurais?
7-Eleven.
7-Eleven, is it from
Does that not seem like how their 7-Elevens
nice,
are?
right?
They're like elite.
Oh, I don't know.
Yeah, they serve like actual food.
Yeah, like
Okay.
quality food. They make it fresh and everything. At 7-Eleven.
Cool.
We need that here.
Not our 7-Eleven.
Yeah, not our fresh 7-Eleven, but like they're back there whipping it up.
Cool. There's another, like I've had like asked this question. Some people might have said sushi, like Japan. So this is a form of reductionism, right? So when you take all this complex culture and just reduce it to their bare things that you just want. It depends on the observer how you want to like simplify things. I think the metals thing in astronomy is that form of, you don't see the complexity that the chemists see. Is just an oversimplification of the culture that is here, and just call them metals. Doesn't do justice, but serves their purpose because there's so much hydrogen and helium. So they call metallicity. So their metallicity and our metallicity will be like very different. Okay, cool. Where was I?
17, group 17.
Okay, yeah. So the thing is, metals are losing electrons to form cations. And let's look into 17. So this is called the alkali metals. Group 1 is called alkali metals. Group 2 is called alkaline earth metals. Noble gases. 17. Halogens. So heard about halogen lights? So halo means salt and gen means producer. So you will see a lot of salt producing elements in here. Chlorides, bromides, a lot of salt. So that's the general idea, the name, halogens. 16, chalcogens. 15, nicogens. You don't have to remember these things. It's just how people who are specialists in these particular areas refer these. Okay. Think about what these three will do.